Hello everybody and welcome to Nuclear Physics Lesson 8. Now in last lesson we looked at a couple of different methods for calculating nuclear radius from an experimental point of view. Firstly we looked at Rutherford's method, which was to try to determine the closest approach of an alpha particle to a gold nucleus. Rutherford showed and Rutherford determined that the initial kinetic energy was all converted into potential energy if we assume the alpha particle came to a stop, zero velocity at the point of closest approach. Remember from electric fields that potential energy is Q1 Q2 over 4 pi epsilon naught r. From that we discussed the limitations of Rutherford's methodology and then went on to look at electron diffraction and the experiment there with the equation R is equal to 0.61 lambda divided by sine of theta min. Theta min there being the angle of the first minimum in the electron diffraction pattern. The wavelength of the electron can be determined using the equation E is equal to hc over lambda. In this lesson then we're just going to be rounding off a couple of things and tying up just a couple of loose ends in order to finish this module off. And therefore this is actually the last lesson in the nuclear physics series. Firstly, for this lesson then, we're going to look at the link between radius and nucleon number. So this is just keeping in the theme of studying nuclear radius. Now I'm going to start off with a statement, and hopefully you'll agree with me with this statement, that the volume of a nucleus will be proportional to the nucleon number. Now hopefully that statement is fairly self-explanatory. The bigger the nucleon number, in other words the more protons and neutrons that we have in a given nucleus, the larger from a volume point of view it will be. Now of course that statement can be backed up with experimental values. If you go and have a look on the internet you will actually be able to find enough values and enough data to back that statement up. Now from a geometry point of view we know that the volume of a sphere, or the equation for it, is 4/3 pi r cubed, and therefore from this equation we can say and we know that the volume of a sphere is proportional to r cubed. Now of course if V is proportional to A, where A of course is the nucleon number, so don't confuse that with area, that is nucleon number from our nuclear notation. So V is proportional to A and V is proportional to r cubed, then it will follow that A, the nucleon number, is proportional to r cubed. If we now take that equation and take the cube root of each side, we see that the radius of a nucleus is proportional to the cube root of the nucleon number. A slightly neater physicsy way of writing cube root isn't by writing the cube root like that, but is by putting a to the power of a third, and those two terms there and there, they are exactly the same, they're just a slightly different way of writing it. And therefore we have the equation R is at the moment proportional to A to the power of a third, the cube root of A. Now obviously we don't like to leave that proportional sign in physics, we like to remove it, replace it with an equal sign and a constant of proportionality. So we're going to do exactly that. R is equal to, and we'll put the constant in a second, there's the A to the third. Now the constant here is called R naught. Now that R naught doesn't have a special name, it's just known as R naught, and it is the constant of proportionality between the radius and the cube root of the nucleon number. Now from a basic graphical point of view, if we were to plot the nuclear radius on the y-axis of a graph and the cube root of the nucleon number on the x-axis, then we would end up with a straight line through the origin, and we can see from the equation that the gradient of that line would give us R0. Now unfortunately R0 is one of these numbers that isn't that well defined. If you look in different textbooks, it's going to give you different answers. In the AQA textbook, which is obviously the main textbook that we're going to use, it gives R0 as 1.05 femtometers. In one of my university books on nuclear physics that I was looking at just before I started recording this lesson, it gave R0 as 1.2 femtometers. So there's a bit of a problem there. We do get slightly different values for R0 depending on exactly where we look. And it's one of those values that is constantly trying to be, or scientists are constantly trying to refine that value for R0 to find a better value and to find the correct value for R0. At least for the purposes of what we're going to be doing, though, obviously because AQA are quoting it as 1.05 femtometers, then we're going to be taking R0 as 1.05 femtometers. So using that equation, R is equal to R0 a to the third, we can now use that to have a look at nuclear density. Now we know that the equation for density, rho is equal to m over v. Now firstly, we can track backwards through the last slide to have a look at an equation for volume. We know that V is equal to 4/3 pi r cubed. That's just the volume of a sphere. We are going to assume that a nucleus is spherical. So if we take r is equal to R0 a to the third and cube it through, we end up with r cubed is equal to R0 cubed multiplied by a. Obviously the cubed and the cube root there will cancel each other out. Volume of a nucleus is therefore 4/3 pi, and then we can substitute in for r cubed with R0 cubed multiplied by a. Now for the mass of a nucleus, we can simply say that the mass of the nucleus is the number of nucleons, A, multiplied by U, which is the atomic mass unit. Now just to remind you from year one, the atomic mass unit is 1.661 times 10 to the minus 27 of a kilogram. An atomic mass unit, of course, is a constant in its own right. What we can do then is we can now substitute these two equations, so we can substitute the volume equation and the mass equation into the density equation. And this is what we get. So density will be mass, well mass is the nucleon number multiplied by the atomic mass unit, and that is divided by 4/3 pi R0 cubed multiplied by A. Now at this point we can see that we have nucleon number on the top and the bottom, so those two will cancel out with each other. And then just to neaten everything up, I'll take the 4/3 and I'll move the 3 up to the top. Therefore the density of a nucleus is 3 times the atomic mass unit divided by 4 pi R0 cubed. Now at that point, when we look at this equation here, if we look at all of the terms on the right hand side, we can see that they are all constant. So 3 is a constant, atomic mass number is a constant, 4 pi are constants, and as we said on the last slide, R0 is a constant as well. Therefore, if all of the numbers on the right hand side of this equation are constants, that's then telling us that the density of a nucleus is also a constant. If we take those numbers then, if we take the atomic mass unit as 1.661 times 10 to the minus 27 and R naught from the previous screen as 1.05 times 10 to the minus 15 metres or 1.05 femtometres, what we can then calculate is that the density of a nucleus is 3.4 times 10 to the 17 kilograms per metre cubed. On to the last couple of slides then, we're just going to round off this topic by having a look at nuclear energy levels. Now, the concept of energy levels you will be familiar with by looking at electron energy levels back in year one when you were looking at quantum physics and looking at quantum jumps and fluorescence and all that kind of stuff in the year one topic. Now, nuclei themselves can occupy different energy levels, and the movement between those energy levels, especially jumping down energy levels, moving back to the ground state and emitting gamma particles, will not be unfamiliar to you whatsoever. It works in exactly the same way as we were looking at with electrons last year. What you can see on the screen then is a basic schematic of cobalt-60 decaying by beta minus decay. Now, cobalt-60 just happens to be a beta minus emitter. The same kind of principles that we're going to look at here work with both beta minus and beta plus, and will work with alpha emission as well. Now, when the cobalt-60 emits a beta minus particle, can move to one of two different energy levels for the nickel, for that daughter nucleus. Now, this kind of diagram is fairly typical of what you'll see for nuclear decays. You can see that we have a couple of percentages here, 99.88% and 0.12%. What that means is that the vast majority of the time, when cobalt decays by beta minus, that beta minus particle will have an energy of 0.31 mega electron volts and will therefore decay into this higher energy level of nickel. A smaller percentage though, 0.12%, will decay by a higher energy beta minus particle at 1.48 mega electron volts and will then decay into a different energy level of nickel. Once that beta minus decay has occurred and the nickel is in a higher energy level than the ground state, the nickel will move back down to the ground state, as we know, by emitting gamma particles. Now, on here we're only showing two of the possibilities, going from the higher energy level to the middle energy level, and then from the middle energy level to the bottom energy level back to the ground state. As you would have seen last year, you can also have a decay where it comes straight back down to the ground level, to the ground state, sorry, emitting just the one gamma particle in the process. Looking at the numbers then, because obviously we know that energy has to be conserved, if this one gamma is emitted, then that will have an energy of 2.5057 mega electron volts, and that's just the sum of the two energies, 1.1732 and 1.3325, that you can see on the screen. If we think about an application then of these nuclear energy levels, the one isotope that you really need to know about for A level is technetium-99m. Now I'll explain what the M means in just a moment. What we're going to start with then is molybdenum, and this is so 99, and molybdenum has a proton number of 42. Now that molybdenum, as you can see on the diagram, undergoes beta minus decay, and therefore it decays by beta minus down to this higher energy level of technetium-99m. Now The molybdenum has a half-life of approximately 66 hours, so just over 5 days for the half-life of molybdenum. When it decays, as we said, into this higher energy level of technetium. Now, what the M stands for is metastable. If we think back to year one, we know that in the vast majority of cases, when we have a nucleus or an electron coming down an energy level emitting a gamma, that happens almost instantaneously. When it comes to technetium, though, this higher energy state of technetium-99, that doesn't actually happen straight away. This technetium-99 has a half-life of just over 6 hours, 6.01 hours. So it actually takes quite a long time for that technetium to decay back down to the ground state by emitting gamma. Now, what that has the advantage of then is that for using technetium-99, it gives us enough time, 6 hours, in order to separate the technetium-99M, that higher energy state, from the technetium-99 in the ground state. There's enough time to separate it and enough time to use it. Now, with a half-life of 6.01 hours, just over 6 hours, as I said, it will decay back to the ground state, and then that technetium in the ground state will eventually decay again. So let's just draw it on here. So that will emit a gamma. It will decay down to the ground state, and then the ground state will eventually, by beta minus decay, decay into ruthenium-99. Now, obviously, we need to think about why we want to do this. What is so special about technetium-99? Well, given the fact that we have this metastable state, and as I said a minute ago, you have enough time to be able to separate that from the ground state technetium and any molybdenum that might still be in a sample. What we can do is we can extract that technetium-99M and form a pretty much pure sample of technetium-99M. At that point, we know that in a sample we will only have a gamma emitter. If we can get rid of the molybdenum-99 and the technetium-99 in the ground state, what we're left with is pretty much a pure gamma emitter. Now, there might be a little bit of technetium-99 in the ground state, but fortunately that has an extremely long half-life. The half-life of technetium-99 in the ground state is around about 210,000 years. So compared to the 6.01 hour half-life of technetium-99M, that is significantly longer, and therefore any beta decay from the decay product of technetium-99M will be insignificant. It will be negligible compared to the gamma that we're going to be having emitted from our sample of technetium-99M. Now, from a usage point of view, technetium-99M as a gamma emitter has big uses in the medical sector. In the medical sector, technetium-99M and gamma emitters in general are used as radioactive tracers. In other words, they are ingested or injected into the body, and using a gamma detector, the blood flow or the flow through the intestines or something like that of the technetium can be monitored and can be studied from there. The advantages of using technetium are that the half-life at 6 hours is relatively short. After 24 hours, so after 1 day, 4 half-lives will have elapsed, and therefore after 4 half-lives we've got only around about 1/16 of the original radioactive sample remaining. Therefore, any radioactivity that the body is being exposed to after 24 hours is already down to 1/16 of the initial value. After 2 days, after 24 hours, after 48 hours, and therefore after 8 half-lives, you're down to less than 1/3% of the initial activity of the technetium-99 sample. So therefore, it decays nice and quickly, it doesn't do any lasting harm to our bodies, and even by the time you've passed it out and your body has dealt with however the technetium has been put into your body, as I said, that decay has really just disappeared off and isn't going to harm our bodies at all. However, at 6.1 hours, it does though give us enough time to be able to trace it as it goes around the body. If we had a half-life of only a couple of minutes, then that sample will have decayed off too quickly by the time it might reach whichever part of our body we're trying to study blood flow through. So therefore, at 6 hours, the half-life of technetium-99m is pretty much perfect for using it as a radioactive tracer. So here is your question now for today. Tin 120 has a radius of 5.49 femtometers. Calculate the radius of carbon 12. Have a go at that as usual, pause the video and come back once you've got an answer. So the trick to this question is to form an equation which actually just sort of discounts R0 altogether. What I'm going to write down then is the initial equation. R is equal to R0 A to the third. And I'm going to rearrange that to divide both sides by the cube root of A. What we're left with then is that R0 is equal to R divided by A to the third. Now, because R0 is a constant, then that will be exactly the same for both the tin and the carbon that we're trying to look at. What we can say, therefore, is that R over the cube root of A for tin has to be exactly the same as R over the cube root of A for carbon. What we can now start doing is plugging some numbers in. Now, so tin is Sn, so I'll put Sn on there, carbon, capital C, just to make sure that we know which radius and which nucleon number are which. Now, given this equation that I've written in blue, I'm going to multiply both sides by the cube root of the nucleon number for carbon. What that gives us as our equation is that the radius of carbon will be the radius of tin multiplied by the cube root of A for carbon divided by the cube root of A for tin. Once we plug all of those numbers in, then obviously making sure that we do the cube root bit for the nucleon numbers, we end up with an answer of 2.56 femtometers. Now, I hope you can see that I chose those numbers sort of semi-purposely. The nucleon number for tin was 120, whereas the nucleon number for carbon was 12. And I chose that nicely, that they were a multiple of 10, so 12 times 10 is 120, just to show you that the radii do scale with the cube roots. So obviously it's not just as simple as saying, well, there's a tenth of the number of nucleons and therefore there's a tenth of the radius. As you can see, that's quite clearly not the case. Instead, we've got a tenth of the number of nucleons, but we've only got just under a half of the radius. So that is something that you just need to be careful of and make sure that when you plug it in, you get that cube root correct in your calculator. So to summarise then, today we have looked at the nuclear radius equation, which is R is equal to R0 A to the third, where R0 is a constant. As we said though, it's not that well known a constant, it's not that well defined a constant, but at least AQA defines it as 1.05 femtometers. A of course here is the nucleon number. Finally then, we looked at technetium-99m, how it comes about from the nuclear decay and the presence of nuclear energy levels, and then the uses of technetium-99m as well. So that's it for this lesson, and as I said earlier, that's it for the nuclear physics topic. I hope you've enjoyed it, and as usual, if there are any questions, please let one of us know.